We're always hearing about how AI can learn, right? But what's actually going on under the hood? I mean, what's the real engine that drives that whole process? Well, today, that's exactly what we're diving into. The optimization algorithms that are the heart and soul of machine learning.
It all really boils down to this one big question. An AI model, it starts out as a total blank slate, basically just making wild, random guesses. But then, somehow, through training, it gets incredibly, spookily accurate. Now, this transformation, it isn't magic. It's actually a mathematical journey of constant improvement, and that's the journey we're going to map out together.
So here's the crucial idea to get your head around. For an AI, learning really just means getting less wrong over time. That's it. Every time it makes a prediction, it checks to see how far off it was. And that error, that gap between its guess and reality, we call that loss. The entire goal of training is to get that loss number as close to zero as humanly, or, I guess, inhumanly possible.
And to measure that loss, we use something called a loss function. The best way to picture this, imagine you're a hiker standing in a massive, mountainous landscape that's completely covered in thick fog. Your altitude, where you're standing, that represents your model's error. The higher up you are, the more wrong you are. So, what's your goal? To find the absolute lowest point, the deepest valley in this entire range, even though you can only see like a few feet in any direction.
Okay, so how does our hiker find that hidden valley in the fog? Well, their very first tool, the original foundational map for this entire journey, is an algorithm called gradient descent. It's the OG, the starting point for navigating this crazy landscape of error.
And you know, the way it works is actually pretty intuitive. First, you just plop your hiker down somewhere random on the mountain. Then, you check the ground right where you're standing and figure out which direction is the absolute steepest way downhill. That's the gradient. Then you take one single step in that direction. And then, you just do it again, and again, and again. Check the slope, take a step. Check the slope, take a step. Until you literally can't go any lower.
Now, our hiker can take that step in a few different ways. They could, say, survey the entire landscape before every single step. That's called batch gradient descent. It's super accurate, but incredibly slow. Or they could just glance at one random pebble on the ground and take a quick impulsive step. That's stochastic, or SGD. It's way faster, but also really noisy and kind of erratic. The most popular method, though, is mini-batch, which is kind of the best of both worlds. It looks at a small chunk of the landscape, giving you a really nice balance of speed and stability.
But, you know, this first map, it's got a big problem. Our hiker is careful, yeah, but they get stuck. A lot. This terrain is full of tricky spots, and that simple step downhill method just isn't always enough to find the true bottom. So engineers came up with a clever way to help our hiker get unstuck.
So here's the deal. The hiker might stumble into a small dip in the ground, and from that spot, every direction looks like it's uphill. So they think, aha, I've made it. This is the bottom. But it's not. This is what we call a local minimum. They're at the bottom of a tiny little pothole, totally clueless that a massive canyon, the real best answer, is just over the next ridge.
So how do we fix this? We give our hiker momentum. Imagine instead of walking, they're now rolling a giant, heavy boulder downhill. That boulder is not going to get stopped by some tiny little dip in the road, right? Its momentum is just going to carry it right through those small valleys and keep it rolling down towards the real bottom.
And this analogy perfectly illustrates the next big evolution in these optimizers. Standard momentum does exactly what it sounds like. It adds a little bit of the last step's force to the current one, building up speed over time. But then you have Nesterov accelerated gradient, or NAG, which is even smarter. It's like our boulder looks ahead to see where its momentum is about to take it, and then it adjusts its path based on the terrain it sees coming up. It's a huge improvement.
So we've given our hiker speed. But what if we could give them intelligence? What if the learning algorithm could actually adapt its own strategy as it navigates the landscape? Well, this was the next massive breakthrough.
This is where we get the idea of an adaptive learning rate. So let's upgrade our hiker one last time. Forget the map. Now they've got a high-tech GPS. This GPS is constantly analyzing the terrain and telling them when to take these huge, confident strides because the ground is flat and easy, and when to take tiny, careful little baby steps because they're on a steep, treacherous cliff. It's changing its own step size completely on the fly.
A couple of key algorithms really paved the way here. First, there was Adagrad. It was a great first shot, especially for what we call sparse data, where some paths are rarely ever taken. but its GPS was maybe a little too cautious and would eventually slow the hiker down to a total crawl. Then came RMSProp, which fixed this. It introduced a little tweak that basically prevented the hiker from grinding to a halt, letting them keep exploring and keep learning.
And all of that brings us to the algorithm that, for most people today, is the undisputed king of the hill, Atom. Atom is basically the ultimate hiker. It combines the heavy, rolling boulder approach of momentum with that smart, adaptive GPS we saw in methods like RMSProp. It's fast, it's smart, and it is incredibly effective.
So why did Atom become the default choice for pretty much everyone? Well, it's not just that it's powerful, it's that it's efficient. It really does give you the best of both worlds, that amazing combination of raw speed and smart adaptability, and it does it all without needing a ton of computing power. That makes it a super robust and versatile tool for a huge range of problems.
All right, so we've been on this whole journey, from a simple hand-drawn map to a futuristic self-correcting GPS. But how do you know which tool to actually pack for your own journey? Let's quickly break down the choices.
Here's a pretty simple way to think about it. SGD with momentum, think of that as your reliable baseline. It's fast, it's simple, and it works surprisingly well for a lot of common tasks. Now, if you're working with really sparse data, like say text analysis where some words are super rare, then Adagrad might actually be your best bet. But for most situations, Atom is your go-to. It's just a powerful, all-purpose optimizer that is a fantastic starting point for pretty much any deep learning task you can throw at it.
So there you have it. The evolution of these optimizers is really a story of innovation, with each new idea building on the one that came before it. It's this amazing journey from a simple set of directions to a self-correcting, intelligent navigation system. And all of it, every single step, has the exact same goal: find the best possible answer as fast and as reliably as you can.
But the story definitely isn't over. As powerful as Atom and these other algorithms are, they're starting to face new challenges with these massive, incredibly complex new AI models. And that leaves us with one final thought. What kind of map, or what kind of GPS, are we going to need for the AI landscapes of tomorrow? What will that next breakthrough even look like?